Great. So, hello guys. Thank you for joining us today on this tech talk entitled Modern Web Architectures. First of all, I'd like to thank Jishnu for his help on these slides. He basically just made them so much better than I did. Such a great job. So I'll start with the modern software architectures. So basically, what are they? So a software architecture pattern is a general reusable solution to a commonly occurring problem, which means that this basically people in the past came upon problems and noticed that these projects with certain characteristics share the same problem. So they figure out some solutions, general solutions, they applied them to them. So basically nowadays engineers, when they see a project with a given characteristics, they think about a given architecture pattern to apply to avoid all sorts of common problems that people faced in the past. They're pretty similar to design patterns, the Golf design patterns and the solid patterns, but they're applied their broader scope, which means they're applied to facilitate deployment and, for example, refactoring services like old services and all. So yeah, what patterns are we going to see? We're going to see the layered architecture pattern, the broker topology, the microservices architecture, and the client-server architecture pattern. There are two other more I'll talk about in the end. So we'll start with the layered architecture pattern. So as its name suggests, it'll be composed by layers. So it is the most common architecture pattern, and it's also called the N tier. For example, it'll be the N will be like 2-tier architecture pattern or 3 based on the application. So components within the layered architecture pattern are organized into horizontal layers. So each layer performing a specific role within the application. For example, we'll have like a presentation layer, and then a business layer, and then some login services, so some login layer, and etc. So each layer in the architecture forms an abstraction about the work that needs to be done, which means that the other layers will have so little knowledge about the implementation details of the other layers. And I'll give this example. You see, for example, there is a request coming to the presentation layer, which is the first layer. And then the presentation layer handles or delegates the request to the business layer. The business layer does some business logic and then handles that request to the persistence layer, which is basically some ODMs or ORMs, object data mappers or object relation mappers, and object document mappers for the OD. Sorry. And finally, to the database layer. Notice also that there is like a bunch of components. For example, for the front end, there will be like the auth component, and for the business logic, there will be like the object model of the different actors of the system, and all of these layers are closed, which means which also means that the presentation layer knows so little about the business layer, implementation details, and so on and so forth. One thing to notice here is that the requests must follow the flow. The presentation layer cannot access the persistence layer directly and cannot access the database layer directly, and we'll see why. Okay, so one of the key, one of the pros of this architecture patterns is this strict rule of not allowing layers to communicate with each other randomly. Why? Because this hides the implementation details and also allows us for scalability. So why? Okay, so imagine like we want to refactor the business layer. If presentation layer access directly the business layer, the persistence layer, and we will change something about the business layer, the presentation layer won't know about the change, and it may eventually break our app. So yeah, we usually we have to follow the flow with this architecture pattern. But sometimes there are some exceptions, like to facilitate the development, probably, or just some, for example, sometimes we need some login services in here, like the service layer. We need to log, but not all layers need to log what they're doing. So some layers can skip or bypass the service layer, but others can't. For example, the business layer has to log and then go to the persistence, Otherwise, the business layer, some components within the business layer can just bypass it straight to the persistence. Leveraging the concept of the open and closed layer helps define the relationship between architecture layers and request flows, and also provide designers and developers with the necessary information to understand the various access restrictions. Okay, so but there is like a problem with this pattern. It's not very agile, and its deployment is it's difficult compared to other like services. Like sometimes the deployment we need to deploy the database on its own, and also we need to deploy the persistence layer on its own and all. So that might cause some problems, but it's very its testability is great, and it allows since everything is isolated, we can test like everything on its own. And every time we refactor one of the layers or update its dependencies or whatever, we can test that with test the new implementation, and we won't really care about the test results of the other layers, since everything is isolated. For the scalability, it's a little because sometimes if we want to add some sort of logic or to one of the layers, we need to make sure that it is handled by other layers. For example, if we need to add some sort of logic in the presentation layer, we have to make sure that the business layer and the persistence layer and also the database layer can handle any requests from the new features from the presentation layer and anything that comes from the presentation layer. Okay, so here's an example of like a general use case. Imagine like there's a screen. Imagine like this Java app that has everything. Yeah, and there's this presentation layer. A customer clicks on the screen. There's like components within the presentation layer that delegates that click handler, and yeah, and then the customer delegate calls the business layer. Business layer creates whatever objects and actors to perform these tasks, and delegates also to the DAO, the data access objects, to the persistence layer. And then the persistence layer will generate the raw SQL queries to run to execute the customer's command. So basically, that's the layered architecture. So now we'll be moving to event-driven architectures. So this is actually my favorite kind of modern architecture because it's asynchronous, and it's basically composed of small components. Every component has so little work to do, and basically they receive an event and they do some business logic, they persist and whatever, and then they publish an event indicating that they're done. So the event-driven architecture is popularly distributed asynchronous, which means it's event-based. It receives an event, does some business logic, and publishes a new event. And the new event will be picked up by other services. The event-driven architecture is made up of highly decoupled single-purpose event processing components that asynchronously receive and process events. The event-driven architecture consists of two main topologies: the mediator and the broker. The mediator topology is commonly used when you need to orchestrate multiple steps within an event through. This mediator topology we won't go through today, but basically what it does is like you have a lot of like the events are not small events; they're just a huge event, and the events basically themselves are composed of other events. So we need some mediator to orchestrate the execution of the events between the small components, between the event processing components. But with the broker topology, we only need one central, let's say, bus to transfer to where we publish like events and receive events through it, and other small components will pick up the the events that are concerned with. They do the business logic and they publish the new events. So basically, we're going to see the broker topology. A broker topology is composed of two components: the broker component and the event component, event processor component. So think of the broker component as just a bus to transfer the event that are published with the payload that comes with it. And the event processor component is just a small, like a microservice that receives the event, do some business logic. For example, we'll give an example in a while. But imagine an Uber-like app where drivers click the on button. Imagine like they publish an event in the bus that this driver is available to receive requests. So a service picks this driver and marks it as available. So that's all that it does. This is one example of an event processor. There's no central event mediator component controlling and orchestrating the initial event. Rather, each event processor component is responsible for processing an event and publishing a new event indicating the action just performed. So here's an example. We've got this event. Once it's published through the bus, the channel, some event processors that are subscribed to the channel will receive the event. If they need to do some business logic, they do their logic and they publish a new event. Other event processor will pick the new event if they're concerned with the payload, do their logic, and then return the response or publish the new event, or just return a response, indicating the end of the chain of events. Let's go now with an example. Imagine a customer wants to change its address. So in the example here, the customer wants to change its address. So there are two event processors, the code processor and the claims processor. So these will run in parallel, which is one benefit of this architecture pattern. And this claims processor will do its job. And then when it's done, it publishes a new event, which calls update claims. And the quote processor does its small job and publishes a new event, which is recut quote. And eventually, they both will fire new. There will be this new event, recut quote, and update claims will be picked up by a notification process and adjustment process. And these two services, probably in this case, will send responses indicating the end of the chain of events. Okay, now arriving at the microservices architecture pattern, which is really commonly used these days. Why? Because, well, generally people start with monolithic app, which is a huge app where all the code is with all the code base, and then they start gradually moving towards a microservices architecture pattern. This is actually said by Martin Fowler, who always encourages this sort of behavior. All businesses should start with a monolithic app. If it grows too much, they will have to migrate to the microservices. Generally speaking, we don't start with microservices because the communication between, like we saw here, we don't know the type of the messages and what kind of events we need, what kind of payload we need for the event for different events. So mainly after we already have like a working app, which is a monolithic app, we move towards a microservices architecture pattern. Okay, so another key concept within the microservices architecture pattern is that it is distributed architecture, which means all components within the architecture are fully decoupled from one another and accessed through some sort of a remote access protocol. REST, swap, or event-based, even event-based. So event-based architectures can also be considered microservices because they have small components and they communicate with each other using events. Okay, the distributed nature of this architecture pattern is how it achieves some of the superior scalability and deployment characteristics. Why? Because simply, if we have like a new version of, for example, an event processor, small component, we just need to deploy the new version and just test that small component. It won't take much resources, it won't take much time, and also probably the users won't even notice the downtime because there will be none. It's just small component, except for the, for example, the components that handle the database. So basically, users, what developers do is that each microservices will have its own database, and huge microservices will handle all the gathering of all the chunks of the database into a data lake. This to gather all the data in one place, but it happens regularly, not like in real time. So in real time, each microservice has its own database, has the data it needs in the database. So we're gonna see like two kinds of it. For example, there are like patterns when microservices communicate with each other using a REST API. They always communicate with each other using an interface. That's a rule, yeah. And the interface is like one of two kinds. It's either a REST API, like imagine like our app needs to communicate with a third party, so it communicates with the third party using like either JSON or some sort of other pattern, other like data structure, and or they communicate with each other using an event. We'll talk about that. So monolithic application typically consists of tightly coupled components. There are a single deployable unit. Yeah, this is the original app that we have, making it cumbersome and difficult to change, test, and deploy, because like the users will definitely notice the downtime, and it's difficult to deploy. We have to plan the deployment and go through with it, just step by step. But with microservices, everything can be tested locally, and each service can be tested on its own and deployed on its own. So there will be pretty much no downtime. There will be no problems with refactoring the service, since all services communicate with each other using interfaces, like we saw here, user interface layer. So that's the advantage of microservices. There will be, like as I mentioned, two variants of this pattern. So there will be the REST-based topology. Imagine like we have a service and it needs to communicate with Google, for example, IBI Vision or whatever. So it calls it with an API. Yeah, it calls an endpoint on Google, and once they're done, they return the response, and we do whatever we need with the response. Or it'll be like a centralized messaging topology. So in this case, as I mentioned before, the example of an Uber-like system. For example, I'm a client. I just send that I need an Uber or something. I publish an event. So there is a broker, like we saw in the event broker topology, event-based topology. And I publish an event that I need an Uber, and a driver like clicks on, that's indicating that he is ready to accept requests. So he'll publish an event indicating that he's ready. And the system, once there are two, like there is a service component that is subscribed to both channels. When he sees an on driver and an open request, he does the matching between us and returns the response. So you see, there's a service that published the on event, and there is a service that the client needs an Uber, and there is another service that does the matching between them. So there are like three services here, and each service is responsible for one and only one thing. Okay, and finally we have the easiest pattern of all, which is the client-server pattern. Basically, we have a monolithic app on the server, and all the clients ask for the sorry. And there's a monolithic app which is huge on the server, and all clients will access this app either using just using REST APIs. Yeah, we can't really use the events since we don't know what pattern, which one. There will be like no event handlers on the server, because we don't know, we don't have any like other services publishing events and handling them. So yeah, basically that's it for the presentation. If you guys have any questions before we move to a quick implementation of the microservices with the broker topology. Yeah.
Yeah, I have a quick question. If you could just, in a quick, maybe summary, tell us, I mean, because you mentioned there's the event-driven, right? And then there's the microservice. What's the main difference between the two?
Yeah, yeah, microservices can use the event-driven architecture. Yeah, so microservices can communicate with each other. So initially, microservices communicate with each other with the REST APIs, but recently they moved to this new pattern, if I may say, using the events. So the event-driven architecture, as we can see here, we can consider the single event processors. We can consider the single event processors as microservices, since they do one job and one job only. But probably they won't have like their own database, because that is the key feature with the microservices, that each service has its own the database. And there will be like another service that gathers the whole data on a data lake somewhere else, and does the caching and the cleaning up of the data. So probably that's the only difference between them.
Okay, so basically, like when you're using microservice, it's similar to the event. The difference is each handler is like its own application or something like that. Like
Yes, but we can also use microservices with REST APIs. So that's that's with the event-driven. There will be only events. Like, so some service firing an event, and another service that is subscribed to the event will cache the event and does the whatever logic that it needs to do. Yeah. But okay. with microservices, we can use both events and REST APIs.
Okay. Thank you. Clear.
Okay. Any other questions? So I know that I moved too fast. No, so I'll just stop sharing and share my my VS Code. Just a sec. Can you guys see VS Code now?
Yep.
Okay, so basically what this app is, there is like a server and there's a client, and they need to communicate with each other using a broker, like just like we talked. The server is totally like it's a package JSON, package log, so it can be deployed on its own, and the client also can be deployed on its own. So here's the server. The server basically is an Express app. So there's the on one just the one router, and this router. Okay, so we'll talk about the publisher in just 1 second. This router receives a body from a, let's say a client, which is Postman or something, and does some and then it publishes the body that it received, publishes, and some other service will pick the new event, that event does some logic, and then insert the logic into MongoDB database. So and Postman will start. Okay, so we'll go through a little bit through the code. So as a broker, I chose Redis because Redis is not only just an in-memory database, but it also can be used as a broker. So I'm just using Redis. And I didn't install it locally, just used Docker for this. You can see. And there is here's the Redis that I'm using. It's called PhazeRo, and it's on. It's ready to receive like events and publishes them. Okay, so we'll go here. Just a sec. Yeah. All right. So you can see here there was just some constants for the channel name and the port where we need to listen. There is also the publisher that needs two parameters: the port of Redis and the host. Where is it? Like, where is it? And then we use the publisher that we created. We publish an event in the channel with the given channel name, and Redis only supports strings, so we have to stringify whatever body we send. Okay, and yeah, for the client, we create a subscriber because we need to subscribe to the same channel name. You see here, PhazeRo, and here we've got PhazeRo, the same channel name. Yeah, and then this is a setup for the MongoDB database. There is a schema for the user, and there is a user model. So nothing much happening there. So when we okay, so we're talking about events. So whenever we see the subscribe event, we log this, and we subscribe to the channel with the same name as the channel from the server. All right. So just a sec. All right, so we've got here the subscribers are listening. All right, so right now what I'm going to do is once we receive a message from a channel, which is PhazeRo channel, we're gonna parse that body because I said like Redis only accepts strings, so body payloads as strings. We need to parse it. We'll create a user and insert it into our database. This is just a basic example of a business logic that we're performing here on the client. So on this, the server will publish an event and returns a response. So for example, we have this payload. Can you see Postman, or do I have to share again?
We can't see Postman. Yeah.
Okay, great. So for example, I'm going to post this payload, first name, last name, profession. So it returns OK from the server. So here's the server. The publish method returns true if it publishes the success, otherwise false. So we've got an OK, and then it publishes the payload, and basically the other service picked up. So we've got this subscriber received message in channel PhazeRo with first name, last name, profession. And then it created the user model, and it added the ID, created ad, and updated ad, the timestamps for that object, and inserted it into our MongoDB database. So this is just a basic example of how a client and a server communicate with each other using events. Yeah, do you have like any questions? This is just a constant.
Yeah, I have a question here. So, so you made just to clarify, you made a request to the server.
Yes.
And then that's how we got the event on the right on the client, right? So the server is configured so that it immediately just responds to that request by sending something to the client, correct?
Yes, sure. Yes, because you see the publisher here has the same like configuration as the subscriber. See, for the port and the host of Redis, and we've got the same here on Redis. And the publisher is about to publish something here. You can see publish. We're giving him the publish the channel name and the payload that needs to be published. And the subscriber is subscribing to once it receives a message from a given channel. For example, there will be a lot of handlers here if we have like multiple channels. If we don't, it's just one handler, like in this case. And you see here, subscriber received message in channel PhazeRo. So here we'll receive all kinds of messages from all channels, and we just need to test which channel are we concerned with. If this, for example, this client is not concerned with this type of event, it just skips it. So yeah.
Okay. And then you did mention because I didn't want to interrupt you when you were first saying you were saying something is a broker. Can you clarify what a broker is in this case and why that terminology?
Yes, sure. It is in this case it is Redis. I'm using Redis. So here.
Okay.
It's just I use Docker because it's difficult to install it on Windows and there will be all sorts of problems. So I just use Docker. So here's Redis. It's called PhazeRedis. And when I started, like I just run Docker run, and we'll give it a name, like a name Redis test something. we do the ports. We need to make sure that the port of the container matches the port of outside the container. So this means that the inside of the container points to the outside of the container. And yes, that's it. So once we run this, we will create a container from the base image of Redis, and it'll be, in this case, our broker. There are other brokers like Kafka that supports like millions of connections and just a small window of time, but they're all like they're not free. We should like pay to use them. So yeah, there's the RabbitMQ, which is free. So yeah, there are other brokers, but this case I just used Redis.
Okay.
I have a question.
Yeah, sure.
You used MongoDB database, and my question is, this architecture forces us to use NoSQL database, or no matter, we can choose each database we want according to the service that we want to provide?
Actually, no matter. It's just that in this case, I had like MongoDB installed on my local machine, and I just used it. So here, we can create whatever like object we want. We can just skip this and just return this result to some other client or whatever. So there will be. And, yes.
Yeah, go ahead.
No, nothing. Yes.
Okay, and also, is it possible we had something hybrid? For example, each services has a own database, and actually there was a shared database for other services.
Yes, I understand.
I'm asking about the data.
Yeah, so we can do that. Yeah, for example, one service can be like implemented using Flask, Python Flask, and another service can be implemented using Node.js or something. And they communicate. The only thing is just that they need to share a broker, and I'm sure like Python has a Redis library or something, and or they can communicate with REST APIs. Was this your question?
If possible. Yeah, I think that's, yeah. And besides, is it possible, for example, if you have a SQL database, just each service that just have access to a specific table or stuff like that? I want to know more about this side, how we can manage the database side of the microservices.
Okay, so usually what they say, like with the best practices and all, each microservice will have the tables that it needs, and to run the job that it needs to run. And there will be like another service that gathers the old data in something called a data mart. And when it's huge enough, it will be called like a data lake, where this service needs to clean the data and insert all the data in that data mart. So.
Right, yeah, I see. Okay, I get it. Thank you.
But there are like some cases, like I know someone, like when I was doing my, well, when I was like an intern, someone told me like there can be like some edge cases when microservices just share database connection, when there aren't many, and the cost of migrating the data between microservices is just too much. So they just share the database.
Yeah, thank you. Makes sense.
I have a question.
Yes, sure.
And in this use case, so we use the microservice as a trigger for the broker, correct?
Can you repeat that, please?
So in this example, the use case, now we are treating the microservice as a trigger for the broker.
Yes. This is the trigger. Publish.
Can we reverse that? Like, no.
Yes, we can, like this subscriber, we can create like another publisher on the client and publish a new event, and the new subscriber on the server, and that subscriber on the server will pick up the new event.
Okay, thank you.
Was this it? Because probably.
Yeah, yeah. Basically, that I'm just converting those to normal REST endpoints, and also in the same time, like how WebSockets are working. So
I think that
it
WebSockets
feels like
is just. Yeah, sometimes it's just WebSockets needs to be open all the time. If I understand it correctly, it needs to be open. But when a publisher publishes an event, it can do other things. Like it publishes an event and that's it.
okay. Thanks.
You're welcome. Is there any other question?
Yeah, it's me again. I promised the last one.
Sure.
So with each pattern, I'm sure, it's all about trade-offs where you use something. I'm just wondering on this particular, with the demo, like what's a real world case where this would be like a possible choice, this type of pattern? Do you have something, and then something that you can tell us?
Yes, to be honest, my graduation project was implemented this way. So we use like a microservice architecture for this, and it was like an Uber-like app. So there was a microservice for the drivers when they click on, they will publish an event. So we made a service that publishes an event to a Redis, and another service that publishes consumes the events, the on events, and creates some sort of a matrix. So there is a driver with its location, and there will be like other when the clients also like request an Uber, there will be like inserted, like they publish an event, and our service will pick up the client's event. They create some sort of a matrix, like we needed to minimize the waiting time. So they create some sort of a matrix, and we use an algorithm to reduce the time using that matrix. So we've made the service subscribe to both the clients and the drivers microservices. So it consumes the drivers, the payloads of the driver and the payloads of the clients. Does the matrix work? Also, it communicates with another Python service using a REST API. So there are like the broker topology, the broker-based microservices and the REST-based microservice. And when it's done, it publishes the final event with the success or the failure into another service that responds to the clients. So this is, I think, a real example.
Whoops, sorry, was talking without I was muted, but yeah, thank you. Okay, super clear. Really appreciate it.
Welcome. Okay, is there another question? So just a quick demo. You can see MongoDB here. Here's our user. We just inserted. So
we cannot see MongoDB.
all right. So
You just see VS Code.
Yeah, just VS Code.
Just a sec. What about now?
It's good.
So yeah, here's the MongoDB object that was inserted. Well,
Just a quick question is, what if let me put it in this way. How about the maintain of the code if we use this kind of architecture? Is it like hard or easy?
Which architecture? The microservices with the broker?
Yes.
Just a second I think it's easier than the layered architecture or the monorepo pattern where all the code base is in one place, because as you can see, the whole service is just here. It does so minimal tasks that it won't be like there won't be too many files or data structures or something. There will be like just some few files, some configuration files and all. So I think the maintenance won't be as difficult as a monorepo where all the code base is in one place.
And what if we like killed one of the microservices and there is broker having an event for that microservice? So
yes. So in the case of Redis, if no one picks an event, it just ignores it. But I know like there are like others where they can raise exceptions and all. If we want.
that's great.
So Redis just ignores. Yeah.
So yeah, that's great. So like it won't be still hanging and waiting for a response from the event. That's
no, yeah.
cool.
I just publish the event and that's it. It's not like we need to wait for that response or something.
Clear. Thanks.
You're welcome. Any other questions? No, I think since there are like no other questions, we can stop. So I thank you all again for joining today, and to the next time.